Hello everybody, and welcome back to another installment of Damage Control Assistant Senior Enlisted Curriculum. I'm Lieutenant Timothy Mueller, and I'll be the instructor for Chapter 2, Lesson 1, where we'll be talking about the center of gravity and moments. Now in the last lesson, we had talked about center of buoyancy, center of gravity, and the metacenter. Now we're going to start getting into the details of how the center of gravity changes, and then that way we're going to be able to solve problems with more detail. So first off, we're going to take a look at what we studied in Chapter 0. If you remember this equation, the coordinate of the center of gravity equals 1 divided by the mass, the total mass of the system, times the summation of each individual mass and each individual coordinate. Now we're going to rearrange that, because I'm assuming you're pretty familiar with moments and everything like that. We're just going to bring that mass over to the other side. So we're going to have the total moment of the entire system equals just a summation of all the moments of the smaller parts. So basically, this just means no net moment. So we have the entire system trying to think about that pivoting lever again. The entire system is pushing one way, whereas everything else is pushing the other way. This is going to help us out in getting a better visual of the center of gravity. All right, this first example, we're going to take a look at that horizontal bar again. Then we're going to move the pivot point, and we're going to see how it can apply in the vertical sense, so we can take a look at how G is affected. So the first here, in the vertical sense, like I said, we have this horizontal bar, and we're kind of thinking of every down arrow as a piece of weight that is affecting the center of gravity of the ship itself. So everything's pointing down, and the center of gravity, if you look at it through this kind of model here, is pushing straight up. All the moments on this side are counteracting all the moments on this side. Now, if you remember from previous lessons, it doesn't matter exactly which point we take moments from, because everything's going to give us the same answer anyway. So if we don't take moments around this pivot point, but instead we move that reference point to a stationary point, which is going to be the keel of the ship, we still have this reacting force G. All these moments are still going to cancel each other out. Remember, all of these are imparting clockwise moments, whereas the center of gravity is imparting a counterclockwise moment. This large arrow here is just the visualization of this right here, the total moment of the system, whereas each little arrow here is just one part of the summation that's over here. From this equation, we know that everything from the total system has to be equal and opposite to everything that is to each individual item in that summation. So now if we just take this and kind of just move the camera a little bit, we can now put it in a vertical sense. So we have the keel down here, which is where we're going to be taking all of our measurements from in terms of distance. We're going to have all of our forces, the individual forces, going to the right, and then the overall system is going to be going to the left. And later on in this video, we're going to see how the center of gravity changes with respect to additions, removals, and shifts of this weight. Just like it works in the vertical sense, it can also work in the horizontal sense. What we need to do is find some sort of a stationary point where we take the references of all of our distances from, and then see how the center of gravity can shift with relation to that. So in the horizontal sense, here we have a vessel that's assumed to be an even keel, and we're going to take our reference points about the center line of the ship. No matter how the weight is distributed, that center line is always going to be a hard and fast point that we can take distances from. So here we're at an even keel. Next, we're going to add some weight to this starboard side. So right now, the center of gravity hasn't reacted to it, but we've added that weight. Now we know that the total system has to now impart some of the moment, because now we have an additional moment over here. In order to do so, that center of gravity has to shift over from our reference point. Now we have this moment here and this moment here imparting a clockwise, this moment here imparting counterclockwise. However, this just by itself isn't enough to cancel out the effects of all of these. So we have to have another moment, and the only way we can get that moment is by shifting the center of gravity over. So where in this the horizontal case, everything moved from the keel, so everything was higher than the keel. In the horizontal sense, everything is either to the left, to port, or to the right to starboard from the center line of the ship. All right, so now that we have that basic model down, we're going to start talking about generally how does the center of gravity move. Later on in this chapter, we're going to find out the exact formulas on how to find exactly how far the center of gravity moves. There's 3 different ways you can categorize differences in weight from one displacement to another. You can have a weight shift, where the displacement is constant. You can have a weight addition, where the displacement increases, or you can have a weight removal, where the displacement decreases. We're going to go through all those step by step. So on the left of the screen, you see I just rewrote that coordinate equation, but rearranged for the total moment of the system equals the sum of all the parts. So we're going to go to the first scenario where we have a weight shift. If everything's done internally to the ship, we're not going to have any change in the displacement. So we have this first loading condition here. We have 3 arrows imparting that kind of moment. Then we have the center of gravity, the overall system, imparting a counterclockwise moment on the system. Now, if we shift this W1 down, the moment of that is going to get smaller. Now we know that the system has to counteract the moment to become precisely the opposite of what it is. If the moment becomes lower because we didn't do anything to the overall force, however we lowered the distance, that means the center of gravity, which is staying the same, has to lower as well to counteract that. So if we keep everything in this keel perspective, the center of gravity is going to shift with a weight shift. So if the weight is lowered, the center of gravity is going to become lower. If the weight is moved higher, then the center of gravity is going to go higher. Next up, we have a weight addition. And in this scenario, we have the displacement increasing. So here we have relatively same thing. We just have some vessel, and now we're going to add a weight to this spot right here. Okay? So you see this large arrow? In adding this weight, that means the overall displacement of the vessel changes, which means the force through the center of gravity has to increase. So you see the arrow here get larger. But now, this part, has a larger moment than what can be counteracted by just increasing the magnitude by that much. So the center of gravity has to, in order to match it, move up towards this weight addition in order to counteract all the moments here on the left side. So, in conclusion with that scenario, with a weight addition, as long as it's not on the center of gravity perfectly, the center of gravity is going to shift up for a weight addition that's higher than it, or shift down if the weight is added below the center of gravity. And finally, the last scenario is a weight removal. It's just the opposite of a weight addition, so you can probably think, okay, I expect the center of gravity to move away from a weight removal, and you'd be right. So here we have this scenario, very similar to what we had up here, and now we're going to remove this second arrow right here in the middle. If we remove that, we're removing that much of a moment, so we're going to lower our displacement, and we're also going to change our moment, because just like in this scenario, changing the displacement doesn't impart enough of a moment to counteract everything that's going on the other side. So in moving this arrow, we take away a little bit from the center of gravity. So it goes from this dotted line, this dotted arrow, to the solid one, which is a little bit smaller. And now, in order to counteract everything, it has to move higher in order to counteract everything that's going on the left side. So in a weight removal, remember, the displacement decreases, and the center of gravity moves away from a weight removal. If we remove weight lower than the center of gravity is going to move up. If we remove high weight, so weight that's higher than the center of gravity is going to shift down. I hope that visualization explained a little bit about how the center of gravity shifts generally when you have a weight shift, a weight addition, or a weight removal. The next video, we're going to talk about the reference points of a ship, the keel, the center of buoyancy, the center of gravity, and the metacenter, and how they all generally shift with relation to each other. Then we're going to get on into more detail about how to calculate exactly how far the center of gravity shifts. And then even further in Chapter 3, we're going to talk about how the metacenter is calculated. And then from there, you're going to be able to solve a wide range of problems when it comes to ship stability. However, until then, I'm Lieutenant Timothy Mueller, and I hope you have a great day.